SPTs. Here is my collaborator. And Xiao-Gang work on the math part of this article, and Professor Gulin Chen and Professor Chenwei Cheng. I will first give a brief introduction of the Hermitian SPTs, and then I will try to classify the non-Hermitian SPT. We start from a free-fermion example, then we do the classification of interacting quasi-Hermitian systems. Here, the quasi-Hermitian means though the Hamiltonian is non-Hermitian, but we still have a real eigenvalue. And then we classify the general non-Hermitian system, which means the Hamiltonian is non-Hermitian and they can have complex eigenvalue. And we will find the unitarity will emergent at the fixed points. Symmetry and topology are two very important parts in kinetic matter, and a lot of phases are described by Landau's paradigm. That is, we have a symmetry described by a group, and the system will have a spontaneous symmetry break, and they will have many ground states. Many degenerate ground state, and topology is also a very important part in kinetic matter. We have the famous, we have the KT phase transition, which is described by the vortex, and we also have some very interesting phases. They are topological orders. For example, the Tori code. And today I will talk about SPTs. SPTs are gap topological phases beyond the Landau paradigm, which means we don't have a spontaneous break of symmetry. However, it still cannot be smoothly connected to a trivial state without a phase transition. Okay, and there are some examples such like the topological insulator and the Holden chain. For free fermion, we have a famous tenfold way to classify the free fermion SPTs. I will give an example. For example, the Wenjie SSS model, they are it is protected by the chiral symmetry, and it belongs to the A3 class. They have a C classification in 1D, and this is also a model. I will take as an example to describe the non-Hermitian SPTs, both for interacting and non-interacting phases, state. And very important concept of the SPTs is we need to find some topological invariant. And in this simple free fermion cases, we can calculate a winding number in the K space. Here we require such a state to be translation invariant, but it's not necessary. But the topology is not protected by the translation invariant. Just for convenience, we need this property to calculate the topological invariant. And if we calculate the topological invariant, we can find that T1 smaller than T2, C equal to 1. and there is one edge mode at each edge that we can see from this spectrum. We have two degenerated edge states, which means there's a topological non-trivial phase. And when T1 is greater than T2, C equal to 0, then no edge state is a topological trivial phase. I think that model is familiar to a lot of people. And if we have interacting, the classification of SPTs are totally different. We need to use a different approach to classify the interaction system. For example, the Jordan chain is a spin one spin chain with anti-ferromagnetic interaction. And for such state, we it's natural to ask how can we understand such a state. We usually describe the ground state of such a state by the matrix product state, which is MPS. Physically, we can see in that big circle, it's a spin one. It's S equal to 1 spin, but we can divide it into two virtual particles. And look here, the black dot is represented a virtual particle which has spin 1/2. And after separated the physical particle into two virtual particles, we can construct a matrix product state. We can let the virtual particle connect by a bond, and they form a maximum entangled state. This is the MPS state, and if we projected it back to the real physical space, we find such a ground state is exactly the ground state of the AKL T state. And so, and if we do that, we can find if we put such a chain on an open boundary condition. At each edge, we have dangling spin 1/2. And so the ground state, at line, we have such a dangling spin 1/2 at edge. We will have a degeneracy of the ground state. So since the different SPTs, different interacting SPTs will have different that ground state will have a different structure of the MPS. It's natural to ask how to classify such phases. We classify the interacting SPT spaces based on the MPS of their ground state. So, so mathematically, it's necessary to ask how can we classify the ground state of this interacting SPTs. We will introduce a projective representation, and because such a state is protected by symmetry, so the physical state must be a linear representation of the group action. However, the virtual state, they can form a projective representation of the on-site symmetry. And if you have any questions, you can just ask. The linear representation means that if we act the group acting on a state and the initial state, they are the same physical state, we can have a difference of a phase. But we know in quantum mechanics, a phase vector can be just regarded as a redundancy. So these two states, they are describing the same physical state. However, the projective representation are different. That means if we act U G1, U G2 to the physical state, it's a different. We act U G1, G2 on a state directly. We can have a different phase here. Such a different phase belongs to U1 because we know in quantum mechanics the wave function are allowed to have U1 phase redundancy. And if the theta term is equal to 0, we just have the linear representation. But as long as the theta is not equal to 0, we have a projective representation, and if theta equal to 0, the projected representation, they cannot be one-dimensional. They must be higher than one-dimensional, which explains the degeneracy of the ground state, which also explains why we have such a dangling spin 1/2 particle at the edge of the Hermitian chain. Yes, the projective representation implies the degeneracy at the boundary, and for a given symmetry group, it's nature to ask how many around the construction of MPS, right? Means how much around the ground state of a system protected by one kind of symmetry. The answer is, for example, in the Hermitian chain, there are two kinds of different ground states that are around, and mathematically we calculated how many projective representation around for a given symmetry. And we can understand the such a picture from another approach, let's say the topological quantum field theory. And this is the partition function of the this is a fixed point partition function of the SPTs, and it has a lot of it has a few properties. For example, such a partition function is invariant on the retriangulation, which means when we move this triangle and re-triangulate it, the partition function is invariant. This implies at fixed point, because at fixed point we have the scaling invariant, and no matter what kind of lattice we choose, the property of the system on the fixed point are invariant. So that's the physical meaning of the retriangulation. And this new tool, we can, in 1+1D, we can regard it as the barrier phase term of the path integral for manifold system. If you're familiar with the path integral, we should remember we have a barrier phase term and the energy term. Because at the fixed point, the energy term is not important because the gap is go to infinity. So we only here the very first term. So here is the we sum all the such very first terms for each set. And Sijk, the orientation of the triangulation. In the Hermitian case, we can regard this Sijk as the direction of time, because for a path integral, if we do a time reversal, we just we go from this way, and now we go from this way. So we change the arrow of this. You can see there is a bound, at each bound there is an arrow. We just change the side of the arrow, and because neutral is the very first term, so it belongs to U1, and the partition function is invariant on the G-action on each set. So that's the property of the TQFT topological quantum field theory of 1+1D SPT. And so with all these constraints, we can calculate how many along the configuration of nu2. This means how many along the fixed point partition function. We can get the same result. They are classified by this group 2 cohomology. And now let's start. Let's talk about our result. I will first introduce the most simple cases, which are the 3 quasi-Hermitian, fermion quasi-Hermitian system, which is the most simple example. And the origin of non-Hermiticity, there are a lot of ways to construct a non-Hermitian system. One way is we can have an effective Hamiltonian of a big system. If a big system is Hermitian and is closed, but if we treat the interaction as a perturbation, we can have an imaginary self-energy, and we can regard such a system as an effective Hamiltonian. And in a lot of systems like the cold atom and AML system, or some system with gain and loss at the same time, we can construct the non-Hermitian system. And there are also a few works about the non-Hermitian fermion system, such as the Fermion have a generalized chain number is defined by the tacity of energy eigenvalues. And Wang they propose a generalized Brillouin zone, and they can calculate the chain number in the generalized Brillouin zone. And also have some classification of the non-Hermitian fermion, and they also based on the K-theory. But so far, there is no classification of interacting system. I will take such a quasi-Hermitian SS model as an example. We can see here at the same set, we have different hopping parameter on the same set for both right moving hopping and the left moving hopping. The parameter is A alpha, and we have at the left moving we have A alpha I, and for the left moving we have alpha I inverse. However, such a non-Hermitian system can be mapped to a Hermitian system with a similarity transformation. And of course, it has a real spectrum. They have the same real spectrum as a Hermitian system. So of course, it has the same spectrum, and for T1 smaller than T2, it has two edge mode, and one T1 greater than T2 is no edge mode. But we should ask the following question: is it an SPD state? It is protected by some kind of symmetry, and do the edge mode correspond to a bulk topological invariant? Now we have for the quasi-Hermitian SS model, we don't have the chiral symmetry, the unitary chiral symmetry. So the quasi-Hermitian SS model now is invariant on the anti-linear similarity transformation. We generalized the definition of symmetry. Now we are allowed it can be anti-unitary similarity transformation. So such an action can be regarded as a symmetry. The answer is yes, because one, if we have a ground state and we act such a symmetry action on such a ground state, we no longer have a U1 redundancy, but we have a C cross redundancy. These two states, say describing the same physical state, if we allow C cross the redundancy of the ground state wave function, the physical state is invariant under such a action. And now we have defined the symmetry of a quasi-Hermitian system. So we are going to calculate the bulk topological invariant. Now we don't have the translation invariant, so we calculate the topological invariant by the trace boundary condition. To do the trace boundary condition, we need to put a system on a closed manifold. So we need to add the boundary term. If we naively choose the periodic boundary term, such a boundary term will break the chiral symmetry.
Can I have a question?
This is the one we defined. So we need to choose the correct boundary condition with respect to our chiral symmetry. And for some special case, like we have a translation invariant, our result just give we can have the same result at one Zhonggat. They calculated the topological invariant in a generalized brainstorm. So so that means we can get the correct topological invariant if we choose the correct boundary condition, which respect the chiral symmetry in non-Hermitian system. This is the trace boundary condition. Physically, just we put the system on a ring, and we can put some magnetic flux inside the ring, and we tuning the magnetic flux from 0 to 2 pi. We can then observe the spectrum flow of the system. So that's it. Trace boundary condition. And with this approach, we can calculate the many-body topological invariant. We can get T1 smaller than T2, we have C equal to 1, and then T1 greater than T2, C equal to 0. Now we can reproduce the bulk boundary correspondence for quasi-Hermitian system. So for such such kind of partial convection system, we still have still an SPT state. Now, what's the physical meaning of such the similarity transformation? We think that's C-cross gauge redundancy. Like we have a global C-cross symmetry, and two-way functions are differ by a non-zero factor. Even though such a non-zero factor belongs to C-cross, the two physical states they still corresponding to the same physical state. And if we do a local C-cross gauge transformation, we can have a covariant Hamiltonian. So if we have a Hermitian SPTs, we can allow it to have a C-cross gauge redundancy. Then it will become a different. The Hamiltonian will be different. It will be non-Hermitian, but the physical meaning, still describe the physical state. Any question about that?
Sorry, the Hamiltonian being covariant, but it would be rescaled by some real numbers.
Yes.
So what does that mean? It means that the energy really changes.
No, the energy will not change because it's a similarity transformation.
Oh, okay.
So the spectrum will not change.
Hello, can I have a question?
Probably missed that part. What's your definition for quasi-Hermitian?
Quasi-Hermitian means the Hamiltonian not Hermitian means H is not equal to H, but they still have the real spectrum. The eigenvalues are still real.
Is there some mathematical criteria that they can check if a Hamiltonian is quasi-Hermitian without diagonalizing it?
Yes, there's a mathematical definition, and we cite it. Yeah.
Sorry, the C-cross gauge transformation is not unitary, right?
No.
Right. So then why the spectrum is not changed?
Because it's not unitary.
Sorry. Wait. Oh, sorry. Just one moment. I think Chengke has a question. Can you make your speaker louder? Then I will mute my. Can you off your mic or mute yourself?
Yeah, I just have a very naive question. So in your Hamiltonian, is alpha real or complex? Is alpha just a phase? Or alpha can be any real number?
Which is alpha?
Music here. Oh dear. Let me mute. What's going on? Is it better now?
Hello?
I don't know how to manipulate that.
Oh, okay.
It's complicated.
What's going on?
退掉了那个。
我退掉了，那你把我弄回去。But you can answer his questions first, or can he still?
He says that alpha. I don't see where is the alpha. Which alpha?
You define alpha. So
you mean the hopping parameter in front of the?
Okay.
Yes, the alpha can be arbitrary number belong to C cross.
let me see if we could.
I answer now. Can you
Maybe.
hear me? No, no. No longer the here, right? Yeah.
Okay. Sorry.
No, he asked C dagger is no longer the Hermitian conjugate of C after transformation. My answer is no, they're not.
C star is not the Hermitian conjugate
No.
of C. He says, is that a problem? That C and C star are not related by Hermitian conjugates.
No, no.
It's not a problem, you mean?
In our framework, especially the classification of SPTs, we don't think it's a problem.
Okay, then is that does that answer your question, or do you have other comments? Right. So he was saying that he doesn't know how to solve the free fermion problem with C dagger. So what would be the commutation relations between C and C dagger if they are not related by Hermitian conjugates?
But they are still related by such a phase factor. So,
oh, okay. You mean if they are, so then the commutation relation, that would be, it would not be C dagger C equals I, it would be C dagger C equals some numbers.
yeah.
Oh, okay, then maybe it is still solvable, except the commutation relation has an overall, the algebra is deformed by some rescaling. Is that what you mean?
Yes.
Okay. Does that answer, does that resolve that problem? It's oh, okay.
Okay.
He said, oh, okay, then please continue.
So let me go ahead.
Yes, please.
我要按吗？
你 play 吧。
哦，就这样吧。
好像可以，好不好？
Okay, so let's move to the classification of interaction quasi-Hermitian system. Now we have drawn conclusions that now for a quasi-Hermitian system, we have a C-crossed gauge redundancy. So the barrier phase is also allowed to be buried in C-cross. 这个蓝调很多，我觉得不太好吧。
哦，好的。
是能放。
Turns out this mixture of real and virtual talks is more difficult than doing a virtual talk. So, look. Oh. Okay, but anyway, just scroll quickly.
我不知道怎么拉。 Okay, so this is an example of interaction quasi-Hermitian system. We add a Coulomb interaction in the SSS model, and such a model still is still quasi-Hermitian system, and it still respects the symmetry, which we just defined, which is not a unitary symmetry. it should be described by anti-unitary similarity transformation. Now we can calculate the so this is just a numerical result to check whether it's still a well-defined topological basis. We still have C equal to 1 at topological non-trivial phase, and this is the gap between the ground state and the first excited state, and it decay exponentially with the system size, and we can calculate a non-trivial topological invariant at t smaller than t2. So it's nature to ask how can we classify such kind of interacting quasi-Hermitian system. Now we can still write down a fixed point partition function. The only difference is that now the new 2 no longer belongs to U1, it's belongs to C cross, because the barrier phase now for the quasi-Hermitian system can be valued in C cross. And the other property of such TQFT is same, but we need to add an additional condition, which is that because the spectrum of the quasi-Hermitian system is real, it still has the time reversal symmetry. We add after adding such an additional condition, we can find now the new 2 still valued in U1, and such a TQFT is still classified by the triple homology, which is S2G U1.
Oh, sorry, I missed what is new plus and minus. I missed the meaning of.
Yes, it's just the potential of the such.
Oh, okay, okay. You mean that they are no longer related by complex conjugates?
Well, they are related by complex conjugate.
Okay.
They are related by complex conjugate because in the quasi-Hermitian system we still have time reversal symmetry.
Okay, but here initially, if you say they are in C cross, if they're C cross, okay, then their norms are not 1. But you say, sorry, and then later you said it is still in U1. Also, I missed that.
Well, if we don't have, look, we have some constraint of such a TQFT, like the invariant on the Peckham move and the invariant on the group action, right? And we add an additional constraint.
Oh, okay.
With all these 3 constraints, we can calculate that the new 2 still belongs to U1.
Oh, okay. I see.
It's just we add an additional condition for the quasi-Hermitian system.
I see.
And so we can conclude that for the quasi-Hermitian system, there are fixed point partition functions still have the same classification of the fixed point partition function of Hermitian SPT. This is how we calculated the group homology. The new 2 is given by the group homology, and they are the same as the Hermitian case. This is for quasi-Hermitian system. Now, Let's move to the classification of general non-Hermitian system and the emergence of unitarity. I still give a very simple example to show that it still belong to a topological non-trivial places. Here we add imaginary chemical potential, which is staggered. And such epsilon is very small, it's a small perturbation. And the Hamiltonian is still invariant under the chiral symmetry. And now the spectrum is can be a compact number. And here we get for a system with compact spectrum, we need to define which is the ground state. We define the state with the lowest real component of energy as the ground state, because if we consider the path integral in Euclidean space, only the real component of energy matters, and the imaginary part of the energy just contribute to oscillation. And also we need to define what is the edge state. For the SPTs, when we say zero energy edge state, we mean there is no gap in real component of energy between the ground state and the first excited state on the open boundary condition. Okay, any question about that definition? So we do some numerical calculation. 1T is this is the gap of the ground state and the first excited state at the open boundary condition. And we can see it's at T equal to 0.4. The real part is almost 0. And it will decay when we close to when we turn the system close to the transiting point. But because scaling fact, we can also think the system is still in a topological. The edge we still have edge state. And if we calculate the topological invariant, we get C equal to 1, T1 smaller than T2. And when T1 is greater than T2 is C equal to 0. But at T1 almost equal to T2, the C is air defined, which means at the critical point, maybe it's a more interesting phenomenon. And both examples suggest the same classification of non-Hermitian, general non-Hermitian systems as the same as the quasi-Hermitian and the Hermitian one. But this is just an example. And now I will go to the partition function to give a general statement. This part may be well, because I don't have enough time, so I just jump this part. A little mess. Just in summary, 2D TQFT is, as long as it's local, it must be unitary. That's a mathematical proof, and I will give a physical construction of the TQFT in the following section. And this is also a mathematical proof. It means it tells us as long as the Hamiltonian is local, no matter if it is Hermitian or non-Hermitian, it must correspond to a 2D local TQFT. And since both if you remember, a local TQFT must have a unitary structure. So no matter the Hamiltonian is Hermitian or non-Hermitian, as long as it's a local, it must have a unitary, it must correspond to a unitary TQFT. So a unitary structure can emerge at fixed point. But this is a mathematical proof. I think it's too vigorous for physicists. So I will give a more physical construction of the fixed point partition function. And we constructed the TQFT by the Frobenius algebra. Frobenius algebra is both an algebra and coalgebra satisfy the following condition. Here, A is a compact backspace. As you remember, when we talk about TQFT for Hermitian system, we put some group at this point. If you still remember, here we don't. But in 1+1D, the equivalent description. When we put the group at the bound, and here we put a backspace on the bound. We can regard it as a gauge theory. And the new is structure. And the new is like this two line will become one line, and this eta is like this to this, and the delta is this part, and the phi is this configuration, and we will see how we reproduce the well-known digraph pattern from this. Let me go ahead. The general partition function of a general non-Hermitian system can be written in such a way. And the F is such a parameter which is similar to mu2. And we sum the we also sum the set, and we times the different f. And the partition function is invariant on the Peckner move, which is the same constraint for the partition function for Hermitian system. And so we can assign omega equal to belong to C2 GC cross is a pseudo-cycle of the group homology buried in C. And we can define a Frobenius algebra, which is called the tracer group algebra as follows. Just we give a special construction of such F and the corresponding Frobenius algebra. If we do that, we can find such a TQFT and classified by H2G C cross. Here the anti-unitary is a little tricky, but so we just consider the unitary group.
Is it still a group H2G C cross?
H2G is a true cohomology. G is a group.
Yes, is this is this still a group? Cohomology group?
Yeah.
He's no longer sharing the screen. It looks like, you see, what I'm seeing here is not the same as what he is seeing on the screen. So some people are complaining.
I'm sorry.
共享错了。
没有切过去。
是。
好的，太多了，看不见，是这个吗？是的。
好像对。
So
Oh, sorry, this room will be taken at 3, so I'm so sorry.
so I will just finish the.
You can, I think we can be late a little bit, but not too much. They are waiting outside.
Okay. So now the TQFT for general non-Hermitian system can be constructed in that way, and such a TQFT is still classified by the S2G cross two cohomology group. And mathematically, we can prove that for arbitrary I greater than 1, that HIGC cross is isomorphic to HIGU1. So the classification of 1 + 1D general non-Hermitian bosonic SPDs is same as the Hermitian one. So here's the conclusion, and we can just see. Thank you.
Oh, sorry. We don't have to hurry that much. I didn't completely get what the last step where it turned where you show that it reduces to
This one?
Yes.
Yeah. We can prove from a short exact sequence, and mathematically these two groups are isomorphic.
Oh, okay. Sorry, why do you call that a physical proof?
Because we have a TQFT, right? we have a TQFT. Yes, I know it's not that physical, but it's.
I see. Are there other questions?
I think they don't. Okay, go ahead.
Sorry, what were you about to say? Okay. Are there other questions? Are there other questions online?
Yeah, we can talk about detail later.
Oh, sure. So if there are not other, okay, so something. How do we define boundary degeneracy? Both the real and imaginary parts must be the same. Both the real and imaginary parts of energy must be the same, or just real parts?
We just defined that there are no gap in real component of the energy, because the imaginary term just can be regarded as inverse of lifetime. It's not matter, so we only care the real part.
Oh, you mean the imaginary part is also it is going to die off, and therefore we don't care?
Something like that, I think.
Okay. Are there other questions? Right, can contact you to ask you directly.
Yeah.
So thank you very much for coming. Someone is coming to this meeting room, so we'll improve on our technology next time. Thank you very much. Sorry about that. Bye.